The crosstalk, so crosstalk effect, we can model that there's a one line there, A, and another line B. Between them, we have a coupling capacitance, C. So typically, to change the voltage between the capacitance, we need to add a charge or extract the charge from the capacitance. So such process requires some time. So capacitor doesn't like to change its voltage instantly because the movement of the charge is kind of finite especially when you drive that capacitor with the current I there. The constant rate of current I is defined by the charge over time, right? Unit time. So it requires certain the time to change its voltage. So when in this kind of a two line structure, if the one of the line moves like the voltage from 0 to 1 volt, then the voltage between the capacitor is like to be 0. So the line B will follow the line A activity like that, and then eventually goes down by the certain driving impedance there. So momentarily, the line B follows the activity of the line A, right? So when the neighbor switches from 1 to 0 or 0 to 1, 0 to 1 or 1 to 0, the wire this voltage propagates through the wire, and then this is through the coupling capacitor, the line next to it. The neighbor also want to see some of the switching activities. This is called the capacitive coupling or crosstalk here. So this is kind of can be thought of noise on the non-switching wire, even though the line B is not switching driven to 0. There's just some activity still here because of the A change. If the A is driven like that, there's just some activity there. The line sees some of the glitches there. This is kind of noise. So if this kind of glitches happen, let's say if we drive the line B with that inverter, line B tend to propagate like that. But if there is a glitch happen when the B moves, momentarily it may go down and go up, something like that. So actual signal may propagate slower. So it may increase the delay on the switching wire. If you have the aggressor, we call this as aggressor noise source. If the aggressor is just next to your line, then with the large coupling capacitance, so your signal will be contaminated. And let's look at the several cases capacitor modeling. For example, you have a layer wire, you have the wide plane above the metal line and below the metal line there. If those two lines are quiet, then you have a C top and C bottom. So because those two lines are tied to, let's say, AC ground, what you see from this line is C top plus C bottom capacitance, right? So total capacitance is like this. Now situation is a little complicated when you have a two line running in parallel like this. We know that physically we know that A have a capacitance to ground, B also has the capacitance ground, and A and B we have a C adjacent coupling capacitance there. So what would be the line A capacitance that would be depending on the activity on the B, because we know that Miller effect, where if we have a capacitance and is the terminal away from, let's say, A and B, we have a terminal there. If the terminal B is somehow driven by some gain, proportional gain from terminal A voltage there, then we see some different capacitance value. For example, if we have a minus the gain there, so let's say we have a voltage on the A is VA, then the other side will be have a minus A times VA, so VB voltage would be like this. So between those two, we see the capacitance across the terminal. We have a voltage VC, so VC become what? VA minus VB, that is VA plus A VA, that means 1 plus A VA. So if we assume that we apply the current IA there, then the amount of current would be how much? So the 1 over SC, we have the capacitance impedance is 1 over SC, and the what? So VA, we know that voltage across the capacitance is what? So the 1 plus A. So the current, we can calculate the current through the capacitance. Current is impedance over 1 over SC over V, right? VC. So that would be VC is shown here. So this current IA, the current going into this IA is that what? So 1 plus A times VA over 1 over SC. So if we rewrite that, the VA over 1 over SC times 1 plus A. So actual capacitance looks like amplified by there, right? So we know the impedance equivalent, G equivalent is IA over VA over IA 1 over, that would be 1 over SC times 1 plus A, right? So it looks like the equivalent capacitance looks like the amplified from when you look at the equivalent, when you find the equivalent the impedance there, it looks like a node, it looks like have a capacitance to ground, and C is 1 plus A, right? This is something that called the Miller effect, right? So considering the Miller effect there, when we have a B is constant, let's say that is constant value that let's say that is tied to ground, for example. Let's say we apply the delta V on the A, right? Like make we switch line A from 0 to VDD there, right? Then the voltage between A and B would be, the delta V would be VDD, and effective capacitance would be from when effective capacitance is the CGND to ground plus C adjacent coupling capacitance here, because B doesn't have any activity, it looks like a ground, so the line A seems like to have two capacitance there. So see, a adjacent capacitance is just seen as it is, so multiplication factor is 1, just multiply by 1. One next strange effect is that when you have A and B moving at the same time, A and B toggling at the same time, they mean delta V is always 0. Then the gain from here to A to B is 0, so there's no Miller effect. There's the by Miller effect. Let's say we have a C 1 plus so from the Miller effect, we call this, if we have a gain of a minus A from between two terminal, then we see the equivalent capacitance C 1 plus A. If the line, those two lines moves together, then A becomes minus 1, right? So capacitance totally disappear, right? There's no no adjacent capacitance, so we only see CGND. However, if we make the B switch differently, like the 1 to 0, different direction, VDD 0, then voltage difference will be 2 VDD between A and B. So the gain of the amplifier between coupling, adjacent coupling capacitance looks like a gain equivalent to A equal to 2, right? This is the opposite direction, right? But the voltage difference 2. So see, adjacent capacitance is amplified by 2. That it looks like a gain there. So by Miller effect, there's a Miller effect, Miller coefficient will be 2. So see, adjacent capacitance actually seen as a 2x larger. So it is important there to minimize the effect of the C adjacent. We see that those three cases is the adjacent capacitance can be calculated differently depending on the switching activity of the B, right? Let's model the crosstalk noise. Let's say the aggressor, we have the line here. Aggressor will have the noise, the activity here. So the victim line next to it, and we have a coupling capacitance. Let's say if we have the voltage transition on the aggressor line by the delta V aggressor, then the output voltage, if the other victim is floating, for example, if that's floating, right? Floating, then if we have a delta V here, how much delta V we see here? Delta V out is, how we calculate? The capacitance. So we can say that since this is floating by the charge conservation, this is the floating, so there's nowhere to go with the charge, so total charge should be the balance, always stays the same. Let's say we have a here, so initial voltage, like this is, let's say charge to ground 0, for example. This is now 0 0, right? So initial charge Q on the output here is 0. That is how much, how you calculate the charge on the, let's say if we have a delta V here, then this will be V out, let's say delta V out voltage. So on this line, how many charge we have here? So charge here, C adjacent will have a charge amount of V out, delta V out minus delta V plus CG and DV. So we have the CG and DV, and between voltage delta V out minus 0, right? So finally delta V out, if you find the delta V out there, then you will get the delta V time over what's dj, and c at dj plus c gndv, right? Something like that. So we have this equation. So if we have a delta V activity on the aggressor, you see the delta V out. The other victim side, we have the additional voltage change that is proportional to this by this factor, right? The CADJ divided by CADJ plus CGND. So larger the C adjacent, the coupling capacitance, we'll see larger coupling there. Now the previous case, we assume that victim is like floating. What if the victim is also driven by the ground through the R victim, right? That is usually typically driven by inverter, right? This is inverter, this line. So this one is inverter modeling there. So notice now, so with the initially the victim will change the voltage delta. Let's say if the aggressor changes delta ADV, then V out, victim side will have a voltage change, but without R victim, it will stay high, but because of the discharging R, so it will go down, right? By the RC time constant that we are seeing here, right? This time constant tau equal R victim times CG and D and V, right? So actual voltage initial peak is kind of related to the resistance between our aggressor and victim side. The time constant, I mean the time constant will have some relation. So if you find that the relationship is like this, so we have a 1 over 1 plus k factor. Here k factor is like the time constant ratio here. So aggressor side, we have a time constant of R times a GND plus adjacent, and victim side we have a GND plus GNDV plus adjacent, like this. So what you remember is that still we have some coupling effect here. So adjacent line will have a different coupling with the R value, right? If the R is stronger than R aggressor, for example, if this R is smaller, stronger mean smaller resistance. So if the R victim is smaller, go approach to 0, there K becomes infinity. So K goes infinity, then the delta V on this line will be 0, right? But typically we have let's say similar driving strength is there. If the R equal to R aggressor and R victims are same, and then we will find out the K equal to 1, right? K equal to close to 1, yeah, approximately 1, then we get the half of the signal we'll see on the line, the victim, right? In the previous case, I explained that the victim will move up and then goes down by time constant. So time constant calculation, I did not calculate, take into account this C adjacent. So it should be R victim, tau should be R victim times CG and the V plus C adjacent, right? It should be like that. Why? Because so here we don't see the Miller effect, because once we aggressor settle to final value, it looks like a AC ground what we are seeing. So this is like this. So what we see, this time constant here, at that time the aggressor line will be stay a constant. So what we see during this decaying waveform, we just see adjacent without Miller effect. So total time constant on this slope should be like this. It is shown in here, right? This is the simulation result of the coupling. So we have two lines, one line driven like this, and on the victim side, if we make it undriven, meaning floating in case, so we drive that line with this signal. The victim will be like almost half voltage settle, right? Half of that. So this is C and this is C. Then the half of the aggressive voltage is shown in here. Now if we have inverter drives, like two lines like that, the device size is equal size 1 to 1, then we get this kind of glitches. And if the the victim equal size driver, so if we have the same size, then this dotted line kind of glitch is happening. So if the victim is half of them, so this is 0.5, victim is 0.5 size, then x1, then we see much larger the glitches, right? So the stronger driving will reduce the glitches, right? But in the first place, we should avoid such kind of cases. If we can avoid this kind of large adjacent capacitance, this is kind of something that we should avoid. So now we had understood the mechanism of the noise on the circuit. So let's say we have like a inverter driving like that, some other signal running next to it. Effect is through coupling capacitance. Our signal is, let's say, contaminated. Let's say X is like contaminated, right? Because of the noise, or right just next to it. In this case, what will happen? If the noise is less than noise margin, this inverter will properly generate the logic value, so nothing will happen. So for the static logic, the beauty of the static logic, eventually it just refresh the output with from the supply, right? So even though there is a glitch at the input, so the internal CMOS logic will replace the input voltage with the supply and ground of each own. So it is clean output is there, right, at the output. So we have a clean output. But this kind of the glitches may cause extra delay on the line, right? And also, if there is a false transition, if the glitch is so large, let's say if glitch is so large there, and output will like make a false transition. So that is kind of extra power from the false transitions. So we should avoid such case. And such kind of glitch is very dangerous for dynamic logic. We have not learned that dynamic logic so far. So what we can say just here is that such dynamic logic is very sensitive to glitches. So we have to avoid very carefully such glitches. And also memory and other sensitive circuits may produce, right, wrong answers. So this kind of glitch should be avoided, right? So wire engineering. This slide will discuss about what is our goal for designing wire in terms of delay and area and power. So we want to optimize those things with acceptable noise. Now, what is the degree of freedom? What we can choose is that we can choose width of the line and spacing, and also we can choose what kind of a metal, what metal layer to use, right? So you will see this delay. So we have a metal pitch and wire spacing. For all these different wire spacings, you get the different RC delay. Well, the wire space is narrower, right? Smaller will get the highest. So you have a line in parallel, right? So you get the slowest, largest time constant delay. And larger pitch, you will get a smaller delay, right? This is line RC, and this is a coupling effect. So coupling is greater when you have a narrower pitch, right? Same. Coupling capacitance is larger, so you get the larger coupling. Those are kind of similarly affect the in order to reduce the coupling, there's some way to use to shield. There's a way to shield the signal. For example, if the A0 and A1 and A2, all these three are the data line, and we want to avoid the coupling between the data line, then we put some VDD and ground shield there. VDD grounds are ideally the low impedance line. So this is the AC ground. So it shield from the. So it removes the coupling capacitance, right? Sometimes we can, if we put all the VDD and ground per each line, then the overhead is so large, area overhead is so large, so sometimes we make it group it like this. Alternatively, we can probably do this, and especially for differential signaling like this, we put things together because the return current path, the differential signal current goes in and current comes out, different directions. So magnetic field canceled each other. So from this current we get this kind of magnetic field, and for this current we get use the right hand rule. So then the different direction, right? So the magnetic field cancels each other, so no magnetic field effect on other circuits. So sometimes we alternate like this. We may alternate things like this. If the signal behavior, for example, A is switching, and the B is like a control signal, so it doesn't switch it, or it just hold the signal, then the coupling will not happen between A0 and A1, right? So the in between the stable control line doesn't move its voltage, so it works as a shield in this example. So there are some different options to play with the metal routings. Now when you consider the wire here, it has length L. The resistance and capacitance is proportional to length, right? So RC time constant, RC delay, now it is proportional to L square, right? This is very large for long wires. So we have to take into account how we are going to handle, how to reduce the delay time constant, R time constant, right? If you have just single time constant there, how we reduce the delay. For example, we have an inverter driving this long line. The delay from here to here, we'll see very large delay. For example, we have a driver inverter here, and wire length is L, a receiver here. This is a distributed model. We can have a N subsection of the RNC, right? RC. Let's divide each line, break the line, make an N section, and add them with the buffer here. So each line will have a smaller length. So if we have an N segment, the length of the line will be 1 over L over N. Each one will be L over N, the shorter. And the capacitance is also shorter. Physically, it's the same wire, but we just break into several pieces. Then what's gonna be delay difference between those two? So typically, the proper number of repeater added, then the delay can be smaller by adding repeaters. So we will see later how we get that result. Now let's go to repeater design. Now the question is, how many repeaters should we use, and how large should be each section, each repeater should be, right? So first, for the long line of wire, we know that it is a distributed model. We break that into N sections, right? And then put in repeater, meaning the inverter, right? Like this, repeats. So each wire length will be L over length over N because of the N section, and the wire capacitance will be L over N times the capacitance, wire capacitance. So this is the wire length per the capacitance per cap per unit cap per unit length. So and the wire resistance also resistance per unit length. So L over N, you multiply that with the unit length. So inverter width, now we know that NMOS device size is W, then the PMOS device will be 2x larger because of the mobility ratio. Now once we determine that NMOS size, we know that gate capacitance, right? The C prime is the unit capacitance per unit width, right? Resistance is similar. So larger the width, we get the smaller resistance. So in this way, we can identify all the resistance on the line and also all the resistance and capacitance on the line, and the input capacitance and of the inverter, and also output driving resistance of the inverter, right? The inverter will drive through the transistor. Each transistor can be modeled as a resistance, right? Okay. So this is the example. So now we use the Elmore delay calculation and trying to find the minimum delay, and what would be the W and N, right? In that way we can find the optimum W and N, right? What we found is that number of minimum optimum unit length is like this, and per unit delay per unit would be like this, and width of the device would be like this. So you can use the previous pi model and try to drive the equation for delay using invert Elmore delay, right? You can easily do that and find it.